Let's go ahead and get started. This is Space City Rocketry's Shasta 6 Flight Readiness Review for May 27, 2023. So for our agenda, we're going to start off with the team introduction, where you'll get a chance to learn more about the Space City Rocketry team. We're going to be going over the Shasta 6 rocket, the design overview, some key measurements, unique features. Next up, we'll have analysis with their flight simulations and relevant statistics. Propulsion, which motor will Shasta 6 utilize? After that, we're going to be going over structures. Caleb will be going over their experiment for this year. Recovery will be going over the ejection systems and parachutes. And avionics will be giving an overview of the flight computers and SRAD projects. So team introduction. We were founded in 2015. SCR is one of two competitive engineering teams under AIAAUH, where we compete annually at Spaceport America Cup. We've competed in 10K COTS a total of 3 times with Prometheus and Oberon, and we've competed once in the 30K COTS category with Zenith. Our long-term goal, however, is to compete in the 10K SRAD solid category. Our primary goals are the following: to design and build a solid propellant 30K COTS rocket with an emphasis on SRAD, given that we are trying to prepare for a 10K SRAD rocket. We're also trying to place in the top 25 percentile and top 5 in 30K COTS at Spaceport America Cup. Our team structure, as you can see in front of you by the diagram. My name is Josephina Arguello. Sorry, I forgot to introduce myself. I'm the project manager for the team.
I can't see your slides. I see you. I see like a screen that I think the slide's supposed to be on, but I don't actually see the slides on the thing.
Oh no. Okay, let me try that again.
Yeah, no, you're good.
Thank you for letting me know.
Yeah, no problem. It was there for a second and then it disappeared.
That's so unfortunate.
If not, good, like a Google slide link or whatever, I can just follow along.
Let's see.
Put it in the chat or something.
All right, can you guys see the screen?
I may be the only one that can.
How about now? Might take a second.
I can see it.
Okay, you can see it?
I'm not sure.
Can you still see the screen, Mr. Christopher Nelson?
No, I'm not seeing anything. I see all you guys crystal clear, but I'm also on my phone, so it may not. I don't know. I see everything but the screen. Yeah, if you just put the slides in the chat, I'll follow along.
I think if you like swipe on your screen, you should be able to like switch views, because I think it may just be like only speakers now on the app.
So yeah, I see you guys on the far right. The middle one has nothing. With you in the top right-hand corner.
Okay, yeah, we can put the slides in the chat.
Yeah, sorry. Every time I swipe over, it mutes me. I see you guys on the far right screen. I see a blank screen with you on the top on the middle screen, and I see a mute button on the left screen.
Wait, Ravi, I think you're muted.
Sorry, I'll put the link in the chat for you. It should be right. You should be able to access that, but let me know if you have any issues with that.
Cool. All right, we're good now. All right, what slide are we on? We're probably on slide number. Well, I see you guys now. Cool.
Awesome.
Okay. So team structure. I'm the project manager. Nice to meet you, Josephina Arguello. Nice to see you again. And then Ravi Desai, our chief engineer. He's wearing the polo. We also have an analysis sub-team lead with Ariba and Leo, the avionics leads Samantha, Aaron, and Orlando, payload with Izzy and Kevin, propulsion with Scott and Parsa, recovery with Christian and Titus, and lastly, structures with Mr. Brandon Broadway. Our team flyer of record and team mentor is Randy Merrick. Our UH faculty advisor is Dr. Sescon. And our mentors are the following: Alex, Emily, Gustavo, Irvin, and Dom. They've been such huge help to the team, and we just wanted to emphasize that they are our mentors because, you know, they've helped create such a huge contribution for us. So just wanted to say thank you. All right, now for Shasta 6, the design overview.
All right, hello. My name's Ravi Desai. As you know, I'm a senior majoring in mechanical engineering, and I'm the chief engineer for Space City Rocketry this year. I'll talk a little bit about Shasta the Sixth, kind of at a broad length, and then I'll let each of our sub-teams go into depth about their specific subsystems that will comprise of Shasta the Sixth. So this is a single stage.
You guys have questions during or after?
I think after will be best.
Okay, cool.
Cool. We are a single stage COTS rocket. We will be utilizing the O3400 motor. I'll let my propulsion leads expand on that as well. We are a minimum diameter rocket, and it is the first minimum diameter rocket that SCR has set out to build and launch. Our outer diameter is at 4.024 inches, and our inner diameter is at 3.9 inches. Our length is at 125 inches. Shasta the Sixth has 3 fins with a wet mass of just under 70 pounds and a dry mass of just north of 45 pounds. Some of the unique features we'd like to highlight this year, kind of on that SRAD component in preparation for an eventual 10K SRAD rocket. We do have a recovery avionics bulkhead, which I'll let our structures lead Brandon expand on. We have the first ever SRAD, a data logging flight computer made up of custom PCBs. We have a biological fruit fly payload experiment. And we've also utilized a carbon fiber and Kevlar honeycomb fin secured to the airframe through a tip-to-tip layout. So these are all unique features that we're embarking on designing, manufacturing, building, and testing for the first time, and we're super proud of these projects for Shasta. So now I'll hand it over to our analysis lead, Leo, to talk about the overall layout of Shasta and then our flight simulation statistics.
Okay, hello. Can you hear me?
I can hear you, yep.
Okay. Hi, I'm Leo Rouge, and I'm one of the co-leads for the analysis subteam. So what analysis does, we don't have our own specific component on the rocket, but we're responsible for keeping an up-to-date model of the rocket and running flight simulations and assisting with ground tests. So that's our job. And on the next slide, we'll have the we have a layout of the rocket. So the layout you see here, this was created on the flight simulation software OpenRocket. And as we said already, the total length is 125 inches, with the nose cone being 19 inches, the upper frame being 46 inches, and the lower airframe being 60 inches. And the material is G12 fiberglass. And dry mass and wet mass, as we've said, the dry mass is slightly above 45 pounds, and the wet mass is just below 70 pounds, and the stability is at 1.8 caliber. And yeah, so as I said, this layout was created in OpenRocket, and with OpenRocket, we're able to recreate the layout of the rocket and assign each component of the each and every component their specific position and weight, which you can see on the right side of the you can see the position and weights of some of the components on the right side of this slide. And these positions, they're with respect to the tip of the nose cone. So the recovery space is 12 inches, the avionics space is 14 inches, with the tray weighing at around 1 pound. The payload bay is 14 inches, and its weight, the weight of the payload is about 8.8 pounds. And by doing this, we're able to obtain an accurate center of gravity. And with the center of gravity, it's then we then use the center of gravity value in a different flight simulation software called RAS Aero 2. And with RAS Aero, using this open rocket model, we're able to then obtain a table of coefficient of drag values or CD values, which we then use in RockSim Pro. And if you move on to the next slide.
Cut up there for a second.
I'm just waiting for the
Oh, yeah.
slide to change, sorry.
I think I'm good.
Okay. Okay, I'm here now. So these flight simulation stats you're seeing right now, this is from a flight simulation software called RockSim Pro. And as I've said, it takes the CD values from RAS Aero 2 to create a really accurate flight simulation model that we believe is the most accurate. And if you see on the left, that left figure, that is that's a graph from RockSim Pro. And with RockSim Pro, we're actually able to run multiple simulations at a time. And I believe and by doing that, we can create a scatter plot of the landing data, which you can see on the right side, on that right figure. And that is all for analysis. Thank you.
All right, next up we have propulsion. We have Scott and Parsa.
Get my camera set up here.
Go ahead. Scott. Scott, if you're talking, unfortunately, we cannot hear you.
Okay, I'm here. Okay, I was having a problem because I was trying to set up my camera on a separate device and I do not know how to unlink audio on my laptop, so I'm sorry, no camera today. My name is Scott Viola. I am a co-lead for propulsion. I'm electrical engineering, electrical engineer entering junior year. So on Shasta, we are using a COT solid motor, the Cesaroni 3400. And we chose it because we have previous experience with it with Zenith last year at Spaceport. And it meets the performance requirements that we need. Now, as you saw, analysis said that it would get us to around 28,000 feet. And it saves cost, and it's the best use of resources for us because we already have the casing, which costs a lot of money just to save on our budget. It was a good choice worth considering, and we decided to use it. So the status of the casing is that we're going to reuse it. Our team advisor, Randy Merrick, approved it for reuse after inspection because Zenith did land pretty hard, but it appears to be in good condition. And the reload kit has been ordered and confirmed and will be shipped to Spaceport. So even with all the supply chain shortages, we do have a reload that will be arriving. Propulsion is set. That's all.
Hey, next up we have structures with Brandon Broadway.
Hello, my name is Brandon. I'm a sophomore mechanical engineering undergraduate student, and I am the structures lead for this year. So as an overview, the components of Shasta that Structures is responsible for this year is the nose cone, the two airframes, the upper and lower, the avionics and payload couplers, which have a completely new design that's new to the team this year. It's based around a rail system, which you'll see in a second. And as Robbie mentioned earlier, a new fin assembly with Nomex honeycomb core and a carbon fiber tip layout. Next, rail buttons, and then a motor retention system. You can see right back here. So first is the nose cone. It is a COTS nose cone from Composite Warehouse. has a 5:1 tangent ogive geometry, and it is G12 fiberglass. The nose cone partially houses the recovery bay, but it also extends into the upper airframe a little bit as well. And we're keeping that on with 3 440 shipments. So the payload bay with the new design, as I mentioned, is based on a rail system. In previous years, we've used the common all-thread rod approach, where it goes through the coupler in 2 places and we sandwich the bulkheads on top. But with this design, we have 4 3/8-inch aluminum rails that are spaced 90 degrees apart on the inside of the coupler. And it allows for any of the components for payload or avionics to easily slide their components in and out of the coupler system. So the rail assembly connects to the airframe through 2 screws that are going horizontally through the airframe into the coupler, and then also 4 that are going into the tops of these rails that will hold the bulkheads on the top and bottom faces. And it's worth mentioning that we have done testing on this, and the rails with inserted helicoils in there as well. All of these tap tools have helicoils installed. It surpasses our expected screw tensile strength. And so all of these screws on the payload bay going horizontally will be 832 screws, and there will be 8 of those. And the ones going vertically into that coupler are also 832s. But the 1/2-inch bulkheads that we are using have 6 screws that are going to be radially attached, which will provide us with a little bit more strength for the moving on to avionics, it's a very similar design, but there is just a few small differences, being the location of these horizontal screws and also the thickness of the bulkhead. So again, we are using 3/8-inch aluminum rails. That will be the fastener points attachment to the airframe. And yes, very similar assembly methods, very similar structure. And next is the recovery and avionics bulkhead assembly. So moving from a 6-inch diameter rocket, which we did in previous years, to a 4-inch minimum diameter, we have a lot less volume and surface area on top of our bulkheads to house avionics and recovery components. So in previous years, we've housed both of those components on one bulkhead, and it was kind of like a shared surface on top of the avionics bay. But due to that decreased surface area on top of our bulkheads, we decided to transfer those into 2 separate bulkheads. That poses a little bit of an issue with the assembly method and just the overall manufacturing and assembly portion of that. So we decided to basically adhere these together or strain them together with a 7 1/4-inch U-bolt. So this is a grade 5 U-bolt. It greatly exceeds our expected force values from the snatch force and from any force that are being used. But as you can see, the top portion is the recovery bulkhead, and so we have a black cover. I guess I'll save that for recovery, which we'll go over that. But we have the recovery bulkhead up here, and then passes through into the avionics bulkhead, and that will attach directly to the avionics coupler through the force screws that I mentioned earlier. Yes. And so yes, it doubles the available surface area for all the components, and whenever those are restrained together, it's just one quick assembly action. You can slide all of that in and tighten in our screws. Oh, yes, and it also is worth mentioning, we have done a static NDA, just to, I guess, see the expected loads in the force distribution. And almost none of that load actually transfers down the U-bolts past the recovery bulkhead into the avionics system. The motor retention method for Shasta is very similar to, I guess, the assemblies used in previous years. It's just slightly different in the fact that we are using a G10 fiberglass plate or disc instead of an aluminum one that we had machined. So the hardware that we'll be using is a 3/8 24 ball thread rod and the accompanying nuts, and that will tighten over the motor retainer that is screwed into the airframe. The motor retainer will be screwed into the airframe with 4 832 screws going radially on that bulkhead as well. And those have helicoils installed similarly to the couplers. There is no restriction of the motor casing in the vertical direction. So we are expecting some slight compression of the components during ascent while the motor is burning. And so we don't want any of that load to go into our, I guess, our motor retainer. It's not that we're not really designing for those forces. So you can grab it. It's like so in its final assembly, the motor retainer will be pushed up all the way to these 2 nuts, but this will be basically free to move. So as soon as this starts to move up slightly, there is some gap for that displacement. But we have 2 nuts at the top, and we will tighten those together to create a lock nut configuration to minimize vibrations and hopefully minimizing the backing off of those nuts. And that will just support the weight of the motor casing after the burning during our recovery descent. So with our composite fins, we decided to go with a non-modular assembly for first time doing these fully composite fins. They have been flight tested by our mentor, Randy Merritt. I believe they went up to about Mach 2. So we aren't expecting to reach that value. So it's very reassuring that they have been flight tested to that speed. So it was a very new manufacturing method for the team. In the past, we've just used composite plates that we purchased commercially and cut those to size. But with this fin assembly, we had a Nomex honeycomb core that is a 1/4 inch thick. We sandwiched that with 2 sheets of 6K carbon fiber. And that is the fin blanks that you see on the right-hand side. From that point, we surface mounted them and gave them some epoxy fillets, and then did 2 layers of a 6K tip layup. And we used fiberglass system 2000 epoxy. The main reason why we used the fiberglass epoxy is because of its tensile strength compared to some of the epoxies that we've used previously. And then also the glass transition temperature, which we have also had some issues with in the New Mexico heat. So each individual fin, we were expecting a weight reduction of about 81%. But after measuring and doing our minor calculations, we found out that we actually got a weight reduction of about 85% as compared to previous fin assemblies, which was very exciting. Next is our rail button assembly. So This is also very different assembly compared to previous years, mostly because the internal reinforcement of our rail buttons is not a possibility, because we're using a minimum diameter rocket. So the motor casing fits right up into our lower airframe, so we have no room on the inside of our lower airframes to reinforce that on the inside of the tube. So we opted for a surface mount method of the rail button, and then we covered that as that hardware in two 6-page sheets of carbon fiber as well. You can see that on the bottom left-hand side. So on the top figure, you can see the base assembly for all the hardware that we're using. So we decided to use a weld nut for, I guess, our fastening of the rail button on their airframe. And we rounded out that flat surface to the radius of our outer diameter. Just to give a lot more surface contact, and to make a look profile against the airframe. So we rounded that out, epoxied it, and then covered it in the 2 layers of carbon fiber. And it greatly exceeds the weight requirement of Shasta. And yeah, we expect it to perform very well. But yeah, so this creates a very good process for making custom components, SR components for structures, because we're actually machining our rail buttons out of Delaware. You can see a version of that on the bottom right-hand side. Yeah, so we have 2 locations of our rail buttons. The top rail button is about 2 calibers, I believe, below our center of gravity, and the bottom rail button is about 5 inches from the aft end of the rocket.
Next up, we have payload. Izzy and Kevin.
Morning. My name is Isabel. I am currently a senior in undergrad. I am majoring in biology. To briefly go over our payload, we're looking to examine the behavior and health of fruit flies before and after launch. One group of fruit flies will be under control, which is a steady metabolic state that is seen naturally. And the other group will undergo therapeutic hypothermia. The point of this is to see therapeutic hypothermia as a neuroprotectant. We are testing our hypothesis that because therapeutic hypothermia is a neuroprotectant, it will improve the viability of the flies in a high stress environment. Therapeutic hypothermia has never been tested in high stress environments. It's usually used as a medical treatment in very steady environments. NASA is actually currently doing research for their torpor-inducing transfer habitats for the mission to Mars, which mimics very closely to our experiment, or our experiment mimics very closely to that. They are using therapeutic hypothermia to induce like a hibernated state in humans in order to improve viability on that during that 7 months of travel. To briefly go over our housing structure that my colleague Kevin will go through more in depth in later slides. From top to bottom, we have our GPU, which is our gel pack unit. It houses additional gel packs that are made custom. Our fly experimental containment unit, which is our FECU. It houses the experiment flies. Our lid is most of our parts are 3D printed out of ABS. Our lid will have our connectors for our pump for our active filling system. The steel will house the experimental flies. Kevin will go over this in more detail later on. And then an insulated housing for the FECU. And then our fly control containment unit is on the bottom, which houses the control flies that are not under therapeutic hypothermia.
Real quick before we go to the next slide, I don't know what you guys did, but I can now see the slides on Zoom. The screen's now like more than halfway, so I can see things now. So if you don't see me following along on the Google slides, I'm not ignoring you guys. I can see the slides now, so.
You said you can't see the slides anymore?
I can, like, I want to unmute myself for something else, and then the screen that was white is now populated, so we're good. If you don't see my character following along on the Google slide link, I'm not ignoring you guys. I'm just watching it on the screen now, so everything's good.
Okay, thank you so much for
Thank
letting
you
us
so
know.
much.
I'm glad it worked.
How do I- Oh,
Sorry,
sorry. Wait.
it's a little slow. There you go.
So to touch on our specimen for the experiment, we are using wild type Drosophilum lanagaster, which is a very specific breed of fruit flies. The organ R type is the wild type is found without any mutations. It is the, I guess, most raw form of this fruit fly. This fly in specific is 75% homologous to humans, which means 75% of the anatomy and genes that we can find on these fruit flies will match up to humans, and we can match a gene to humans and observe things very closely. If we were to extract DNA and do PCR testing, we'd be able to find on the exact chromosome what matches. Our control group is housed in the FCCU, as was saying, and the experimental group undergoes therapeutic hypothermia in the FECU. Our specimen analysis and observations, we're looking to observe these flies before and after launch. The anatomy of the flies have been examined at normal states as well as under therapeutic hypothermia. Looking at their central nervous system, their brain within their head follows through a central nerve that goes through their thorax, which is in the middle right before their wings. We've seen that their head tends to bob down a little bit out of protection, usually from the cold, and also just going into like a homeostatic state. This links very closely to their wings, which is more of the musculoskeletal system. As those wings tend to curl up a little more, it almost protects it, kind of the way that your muscles will tense up when you get cold, and like goosebumps form. This protects them from getting stuck on things. A big problem with flies is when they tend to get stuck on things, they either can't move after on or they can't fly afterwards. So we're expecting for the cold to protect that, and then also their heart line that runs very closely underneath, that's also in their abdomen. We've also noticed some consistent behavioral cues that are observed whenever they undergo therapeutic hypothermia. So they tend to huddle towards food as an intention to warm up and maintain a certain metabolic state. As they start to cool down, they settle in a little bit more. Sorry, it just said our internet connection was unstable, so if we cut out, just let us know. But they will start to steady out, and as they warm up, it's usually at a very steady rate and controlled rate. So we don't see too much. We will see them eat a little bit more after they warm up just to get their bodies going again. So one thing that we can use to measure is we will have a screen between the flies and their food, just so that under those G forces, they don't get like stuck into it. But it is expected that the flies that undergo therapeutic hypothermia and come out will eat more food than the ones that weren't in that state. And we also use anesthesia for these flies, especially for transport, in order to make new subcultures, transfer them into their experimental vials, and that is through carbon dioxide and a specific tube process. It's actually very easy to do, and we are able to transport it, thankfully. I will let my colleague Kevin introduce himself and go into more details on the next slides, and I will be able to pull up the components in person as he presents.
Hello, my name is Kevin Tran. I am a senior mechanical engineer and I am the other payload lead, co-lead. I'll be giving you a quick overview of each of the components within the payload. The first component I'll be going over is the flight control containment unit. This section is pretty simple. It will house the control flies and it will have the flies experience the ambient temperature as it is without any cooling system. We're using a screw lid designed to secure the vial within the container, and then everything as you see is printed with ABS. Izzy is showing the part in the camera real quick. Yeah, next slide, please. So for the next section, this is the fly experimental containment unit. This will house the experimental flies, as you mentioned earlier. Since we need to have the flies at a lower temperature, we are including a passive and active cooling system within the FECU, which I'll go over more in the next slide. Can you go back real quick? Sorry. To incorporate our cooling system, we're using quick disconnect tube connectors that will be epoxied into the lid and the holes, as you can see in the 3D CAD. In order to create an airtight seal and keep the temperature within the container, we'll be using a gore sealant between the lid and the steel component. And for the materials, we're using ABS for the lid, the screw lid, and then steel for the bottom half of the FECU. And then for our insulation inside, we're using aerogel. Next slide, please. So for our cooling system, we're using both an active and passive component. The active component will be for the ground phase before the rocket launches. It will use a tube and pump cooling system that will continuously circulate cold water from a cooler into the FECU. Once we're ready to launch, we'll quickly disconnect the tubes through the tube connectors, as Izzy is showing, and then we'll be all prepared for launch. For the passive component, this will be to maintain a cooler internal temperature within the FECU. We're using an aerogel insulated steel enclosure to keep out the high temperatures and contain the cooler temperatures. And we're using a cooling gel pack within the container to help reach those cooler temperatures. In order to monitor the temperature within the FECU, we are using the TempoDisc Bluetooth temperature sensor and data logger that will continuously log the data for us, and then we can download the data afterwards through our phone. Next slide, please. For the testing that we've done preliminary tests for the active and passive cooling. With our active cooling, we did a test at room temperature at 75 degrees Fahrenheit. And it brought the temperature down to 66 degrees Fahrenheit and maintained that temperature for the 2 hours that we tested it. For the passive cooling, we tested it in a thermal oven at 110 degrees Fahrenheit. And we saw that the temperature within the FECU increased from 42 degrees Fahrenheit to 58.2 degrees Fahrenheit over the span of 1 hour. The active cooling was done with only the active cooling, and the passive cooling test was done with only the passive cooling. We haven't been able to test both systems at the same time yet, since we still need to epoxy the base of the FECU to the steel component. So hopefully we'll be doing that test within the next week. Next slide, please. So the final component will be the gel pack unit. This section of the payload will just house additional gel packs in order to help lower the temperature even more. It's a pretty simple component, but this section used to house the electronics for the payload, but we determined that the electronics aren't necessary for our payload. So we repurposed this section for the additional gel packs. This section will be on top of the payload bay and on top of the FECU. and it will be completely printed out of the ABS. And that is it from payload.
Lovely. Next up, we have recovery with Christian and Titus.
Good morning, guys. Can everybody hear me all right?
Yes, sir.
Alrighty. So as Joe just mentioned, my name is Christian Rossi. I'm a senior mechanical engineering major here at the University of Houston, and I'm one of the recovery leads this year. Next slide, please, Joe. Thank you. Just to give you a brief overview of the recovery configuration for Shasta this year. So we're going to do a single bay dual deployment design, which has been done similarly in previous SCR configurations in the past. We'll achieve airframe separation by a primary black powder and secondary CO2 ejection system. Our drogue deployment configuration consists of our 24-inch free shoots elliptical drogue with a calculated descent rate and snatch force of 147 and 19-pound force, respectively. Our main deployment will be considered started by 2 L2 tender descenders in a series configuration, and it will consist of a free shoots Iris Ultra 7-foot drogue, 7-foot main chute. And we'll have a descent rate of 21 feet per second and snatch force 144-pound force. Next slide, please. Thank you, Izzy. Our ejection system, just to go over the two. So for our black powder ejection system, we've developed in the past a high altitude centrifuge configuration, which is basically, if you can see the little plastic centrifuge tube wrapped with electrical tape, it's contains black powder inside of a 20 milliliter little plastic centrifuge tube. Inside that, we put 1.8 grams as calculated to achieve a separation force of 150 pounds. That's really to just shoot off 3 440 shear pins with a factor of safety of about 10 pounds per shear pin. So we stuff the centrifuge tube once we've inserted the black powder with wadding paper and then wrap it very tightly with electrical tape. We'll then insert it onto the bulkhead into a little PVC pipe, and we'll wrap that again with more electrical tape just to keep it in place. Our Raptor, our CO2 ejection system, will use a 24-gram cartridge and is also mounted, as Brandon said earlier, onto the recovery bulkhead. The recovery, the cartridge will screw into the bottom of the bulkhead, and it will just then be stitched tightly onto the avionics bulkhead below. Next slide, please, Izzy. Thank you. So to go over our tender descenders, they're definitely the most confusing part, at least in my opinion, of the entire recovery configuration. So it's going to use 2 L2 tender descenders in series. They don't look like they're in series. You can see from the photos there on the right, and from the configuration is holding up. They are indeed. So in the past, we used them straight up in series, so like one in line next to the other. Our problem that we've encountered with that is if the top tender descender ended up not going off, the E-match would still be connected to the terminal blocks below, and the main cord would inevitably become longer than the E-match itself, so it would pull the E-match right on off. Obviously, to eliminate this failure mode, we've designed this system this year. So it basically just uses 2 separate lines of half-inch 2,400-pound Kevlar to kind of wrap around one another and go through a top hook link that connects to the drogue parachute. The cords will be retained onto the bottom of the main cord, and then directly to the E-bolt itself once the tender descenders actually engage, as you can kind of see when Izzy's holding it up there. And just to note, the tender descenders will be covered by a Nomex blanket to decrease the chance of any black powder damage to components. All right, thank you, Izzy. Next slide, please. We did conduct some ground testing with the tender descenders. As you can see there, it was pretty successful. We used 40 pounds of weight to simulate the dry weight of Shasta, and we used 0.2 grams of black powder per tender descender. I'm not sure if we want to play that video. I'm not sure if it's going to show up for you, Mr. Nilsson, but oh. Yeah, so it's a little hard to see, but the cords ended up coming out of the top tender descender, which is roped onto the post there. So that would just pretty much to simulate the line being broken between the main and the drogue. That would allow for main deployment. Drogue being on top of the main would pull it out of its bag. Everything would be pulled in line. You would only need 1 tender descender to end up actually separating a force. Next slide, please, Joe. Shot cord. So we pretty much have 3 main lines of shot cord to worry about. So this is our drogue configuration diagram. You can see off to the right here. So in blue, we have our drogue line. So it's going to be a 30-foot, half-inch, 6,000-pound Kevlar line. Main is going to be 40 feet, also a half-inch, 6,000-pound Kevlar. This one's going to be a shock loop. So it's going to have its own shock ends on it, just for extra durability of the cord. Our nose cone cord is going to be 30 feet. It's going to consist of half-inch, 3,000-pound Kevlar. And our tender descenders will have each those 2 lengths of half-inch, 2,400-pound Kevlar. We designed the lengths to be at least 2 to 5 times the airframe length. We set it on 3 times just for safety. And these cords will be ended up flaking using rubber bands just to absorb some shock, to release the flakes, and to ease packing organization a little bit in the nose cone. Next slide, please, Joe. Lastly, our parachutes. As mentioned earlier, so our drogue is going to be a Fruity Shoots 24-inch elliptical. So it's going to be the first chute there on the right. We ended up getting a red and white chute, which unfortunately matched our red and white main. We're in the process of returning that now just to ease the process of identifying recovery events between the main and the drogue when it's actually in the air. So it's going to be a coefficient drag of 1.55, and with the descent rates and snatch force, as mentioned earlier. It's going to be attached to a 1,000-pound swivel, and of course will be connected with a Nomex blanket and kind of burrito wrap to prevent any damage to the chute prior to deployment. Our main chute will be that 7-foot Irish Ultra from Fruity Shoots, coefficient of drag 2.2 with the descent rates and snatch force listed. It's going to have a 3,000-pound swivel and will be contained within a Nomex deployment pack. I believe that is it for recovery. Thank you, guys.
All right, next up we have avionics. The co-leads are Samantha, Aaron, and Orlando. In person, we have Aaron and Orlando.
Hi everyone, my name is Samantha Tobias Leja. I am a biomedical engineer major.
My name is Orlando. I'm an electrical engineering major. My name is Aaron Wright. I am a recent computer science graduate.
May you please go to the next slide. Okay, so this is avionics overview. Our main goal for avionics this year will involve electronics igniting charges to deploy the recovery parachutes, collect data with our flight computers and transmit telemetry, utilize a ground station to collect telemetry and track the rocket's location using GPS and telemetry, and fly modular SRAD flight computer to record data and transmit telemetry. As you can see to the right, that's our avionics mascot. Next, please. So this is our ground station. The purpose of our ground station is to receive telemetry from avionics for GPS tracking and data. It is also designed to interfere with both COTS and SRAD flight computers. The functionality of the ground station is that it uses 2 Yagi antennas. One is for 433 megahertz telemetry by altimetrum, and the other one is 915 megahertz SRAD telemetry for our XV. In addition, our ground station has a Raspberry Pi with OLED display screen that showcases the altimetrum software. All of this is stored in a red case as shown in the slide for easier transport. Next, please.
Okay, so for our primary flight computers, or at least our positive flight computers, we will be using an altimetrum as this satisfies the conditions needed for a solid flight computer. It's capable of data logging, barometric sensors, GPS, and it's very low power, only at meeting a 3.7 volt life battery. It functions at 430 megabits on that telemetry, which is suitable for the Yagi antennas that we have, and also very long range deployment. And for our redundant flight computer, it's satisfying the same conditions as our Telemetron and being a backup flight computer with the same functionalities. Again, low power, long range, and it's capable of our data logging and GPS tracking that even when we have a rocket. So for our extra flight computer, it's going to be our third flight computer in our avionics bay. And the two main purposes of this extra flight computer is to log really high quality data during flight and also transmit GPS data as a tracker. So as you can see on the pictures, our extra flight computer is composed of 3 separate PCBs that stack on top of each other with headers and standoff connectors. So the radio on this flight computer uses 950 megahertz for telemetry, which is going to be beamed to our ground station. Some of the sensors that it features are high accuracy barometer, 2 inertial measurement units, a high G accelerometer, and a 3-axis magnetometer. All this data will be logged locally into the flight computer, and it will transmit some of that data to our ground station. So as we mentioned that in the ground station, we are going to be using 2 separate antennas, both of them COTS, but the 950 megahertz antenna will be used for the SRAD flight computers, and our 433 megahertz COTS antenna will be used for our telemetry. For our avionics tray design, we decided to separate the 2 COTS and the SRAD systems. So on the bottom, we have the SRAD PCBs, and then on the top, we have the tray with the batteries and the COTS computers. This allows us to have really clean wiring, as we have no wires coming up and down through the middle of the SRAD flight computers. So we 3D printed this bay out of ABS plastic. On the back, we have the 3 LiPo batteries mounted. On the side, we have the screw switches to turn on each of the flight computers. And then in the front, we have the telemetry flight computer and the EC Mini flight computer.
Okay, now for ground testing. So as you heard us mention earlier, we did some ground testing this year. We actually did 2. First one, not so hot. Second one was a lot more successful. The first one, we gathered all of the items from the SCR lab. So we came here to the lab that we have at the University of Houston, packed up all of our items, put them in the car, and transported them safely using a checklist. After that, so we have a procedure/safety document for the ground testing. I'd be more than happy to share that with you. Robbie, would you mind sharing it in the chat if you get a chance? The testing procedures are in the safety document, kind of lists out all of the steps that we will follow and that we follow during ground test. The items were airtight, so the results are valid, even though it's not an actual flight test, because one, the items were airtight, and the avionics bay and avionics recovery bulkhead were secured to the airframe. So what was tested? We tested out the tender descenders, as mentioned earlier, with the 0.2 grams of black powder. As you can see to the right, the very top one was our black powder test. We used 1.8 grams, and then we also had a CO2 Raptor test with the 24-gram cartridge. So the results for the tender descenders, the results were expected. We used around 40 pounds to test the system. For the CO2 Raptor, the first time the results resulted in an unexpected outcome in which the avionics bulkhead, or sorry, the avionics bay was pushed out. However, we did find a flaw in our design, which we quickly fixed and got that situated. We used Loctite instead of just regular tape as well. So we ensured that the system was airtight. So the second time around, everything worked perfectly fine. It went a lot smoother, and I can go ahead and show you that right now. So I'm gonna play that again. Boom, there you go. Results for the black powder. the method was to start with the smallest amount and move up from there. So we tested out the 1.8 grams and figured out that that worked perfectly fine. So we stuck with that. We tested the system twice and both worked perfectly fine. So the system is ready for spaceport. There's a video of that right now. And one more time. Bam. All right, cool. So we've got that situated. If you have any questions about the ground test, please let us know. We'd be more than happy to answer. Okay, and our final points. Robbie, take it away.
Yep. So just to be totally transparent with you, we would like to just outline the major to-do items that we have left. The team is 100% confident that we'll be able to complete these items in time in preparation for Spaceport America, considering the amount of time that we have left for competition. So for our payload subteam, as mentioned before, we need to epoxy the bottom lid to the experimental control unit. We also need to sand down the steel tube just a little bit more to fit it within tolerance so that it can nicely slide onto our rails and fit within our coupler. For recovery, as mentioned as well, we need to exchange the drogue parachute. We just need to swap out the colors due to IREC regulations. The order has already been processed, so we're just awaiting the arrival of our new parachute. And then for structures, we just need to drill the vertically aligned holes that will go into the rails from the top through the top payload bulkhead. Lastly, our paint job. As you can see, our rocket has not been painted. However, we have a longstanding partnership with a local company called IA Coatings. We provide them with a design and they complete the painting of our rocket. We've gotten rave reviews from all of our times at Spaceport. So we're really grateful to partner with them. They've given us a 1-week lead time and we are going to hand off Shasta to them this coming Tuesday after the Memorial Day weekend. After we receive the rocket back, we're just going to practice and run through our assembly, focus on some dry runs, modify our checklist as necessary, and get everyone really familiar with that process so that when we go out to Spaceport in the heat, we all know what to do. It's on the back of our hands and the checklists are just there to guide us. So once again, we're extremely confident that we can get all these items done in time for Spaceport, and we're excited to launch and see what Shasta can do.
Lastly, we just wanted to say thank you to all of you who helped us, our team mentor, our alumni, our professors. Thank you for helping us with your knowledge, logistics, advice, and financials. We could not be here and we would not be able to do it without you guys. So thank you so much. All right, now for questions. Do you have any questions for us?
Yes, I do. I'm going to start up probably the most pressing and important question. Is the Squishmallow Avionics mascot going to fly on the rocket?
Sorry, can you repeat that one more time?
Is the little avionics mascot going to fly on the rocket?
With your permission, yes, we can duct tape it to the side of the rocket.
Maybe not the side, but cool. Okay. All right. I guess I'll start from the bottom up. I guess the steel tube are going to sand down. So I mean, you have what? 6-inch tube, and you got a 6-inch piece of steel tube, I'm assuming, right?
I'm sorry.
So on the last two slides, you guys talked about sanding a tube or sanding a steel tube to fit inside the rails, right? Where is that here? Yeah, the payload, sanding steel tube within tolerance. You're planning on slotting that tube as a coupler, right? Is that correct?
Steel tube will slide onto the rails within our coupler. Can you get the tube?
Oh, okay. I get what you're saying now. Okay. I would make sure if you're sanding it and you're trying to get a tight fit, do it out in the heat. That way you get that. Well, if you're getting a close fit and you're using steel, it's going to expand, right? And so Oh, hold on. Let me see now.
Thank you so much. That'll help. We've been spending hours on end sanding it with our belt sander.
Yeah, and in the AC it's nice, but once you get out in the in the heat, it's gonna pop a little bit. And if you might want to just do a quick pass on the inside of your coupe as well, where your motor goes at, because the aluminum is worse for that. So just preventing a lot of, you don't want to stand out in the desert. That's never a fun thing to do. This drag coefficient on your parachutes. So I'm just telling this to all the teams. Parachutes is better. Rocketman is worse when it comes to providing accurate CD values. As long as you do a drop test or whatever you want to do, right? Or even better, use whatever weight they recommend. But my point is, don't rely on the CD values on the websites because they're almost always wrong. So if you are relying on the chart that says X parachute for this pound, that's totally fine. But if you guys go on next year and build a rocket or whatever, and you're trying to do your own drag calculate or descent calculations, just keep in mind those are sometimes funny. Your CO2 cartridges. Oh, I'm muted here. No, sorry. Okay. So the CO2 cartridges. Your black powder is your primary, correct?
Yes, sir.
Okay. And you tested black powder charge and it worked well. You tested CO charge and it worked well. Is the CO2 charge, backup charge, sized for a half opened or half deployed scenario? So let's say the black powder charge deploys, something weird happens, it only comes halfway out the tube. Is there enough push in that CO2 cartridge to push the rest of the parachutes out?
So the way it was sized, at least in our calculators, was to kind of get the equivalent amount of force as the black powder, as if it was the only ejection method being used to push everything out. When we were doing our ground test, obviously we didn't have the time to pack everything inside and then kind of see,
Sure.
friction wise, everything would fall out. But theoretically, it should be enough just by itself, 24 grams. I think our calculator said 8 grams should be sufficient, just for a factor of safety and for some experience and troubles with working with CO2 in the past. We're gonna go with that 24 gram.
Cool. I don't know what this note here means. Are you gonna have a pump on the rocket, or is that pump gonna stay on the ground?
The pump will be on the ground, so the active cooling system
Okay.
is like a phase part. We have an access panel, so that we'll be able to unplug the pump and then just screw that on.
Okay. The only point I was gonna bring up there, another team had the same issue, and this is for future reference. This is for this particular project right now. But if you put a pump as your payload, that pump actually makes a moment, and you can actually get some funky spinning on your vehicle that you're not intending to have. So I mean, it's a ground support equipment, right? You're fine. But if you guys next year or whatever planning on doing some cooling with a pump, I mean, these pumps are kind of tiny, so I don't think it's too big of a deal. But it's something to be aware of, especially if you're going to go out in industry. They have systems like these on there. Just keep it in the back of your mind that pumps will, excuse a moment, that will make your rocket spin. Lots of crash things out there. Cool. The sealant for the payload. Do you guys need to keep pressure in that container? Is that correct?
We do not.
Sort of gore sealant.
Yeah, we're looking for an airtight seal just to maintain a steady temperature. Pressure is negligible in the experiment.
Okay. Do you know how porous that print's going to be?
I'm sorry,
You know how porous the print's gonna be?
how porous? What is our?
Yeah.
Yeah, so the gore sealant isn't a true airtight seal. It provides like a good enough seal for temperature, but it still allows that pressure to be somewhat equalized. So we're not concerned about having like a pressurized container as the FPCU.
Okay, cool. Again, you guys get industry in a couple of years. You know, put the back in the face or whatever. The little purities of the prints actually leak out and actually causes significant issues. So like if you're flying on a Blue Origin or a New Shepard flight, you need to prove that, well, A, your stuff didn't degas, but you know, 3D prints aren't necessarily, even metal 3D prints aren't necessarily vacuum tight. So of course, for this application, you're fine, obviously, right? If you guys know that. But just again, keep your toolbox when you guys get out in a few years. Do you know the max G-force a fruit fly can withstand?
The max G-force, so when you kill a fly, it usually smashes around over 125 Gs.
Okay. You guys can get some play there in your G's there. Cool. Yeah. I work with a group that they fly on several rockets at a time, but some of their cells, some of their bio payloads die at 4 Gs. So that's why I mean, fruit flies a little, yeah, it's a little strong. But again, just have it there. Cool. I like the railgun thing. I haven't seen that method of putting a railgun on a linear because your modularity. So it sounded like you guys want a system where you can just like almost like Legos, right? You put some stuff on, take some stuff off. Have you guys looked at what like a Black Brant does for its assembly and modularity? Okay, so what you guys have is great. I'm not bashing on that. I'm just a lot of I'm telling teams. So what they do, they basically have little cans. Each of those cans have a radar connector on it. And so basically you have this kind of common can, and you can put your payload in one can, put your avionics in one can, you know, et cetera, et cetera. And you basically just fasten them together. It's a similar idea of what you guys are doing. It's just another take on that. So I'm not saying that you haven't done and change it. Not at all. I don't believe that. I'm just next year just one of those options and see what's out there. That's been kind of my preaching to all the teams I've been talking to. See what's out there. But you guys did a good job on that. So that's really all the big things. So I didn't see anything major. You guys weren't able to fly this year, which is probably sucks for you guys. I'm sure you guys want to fly a lot, but I know those 3400s are not cheap. So but you guys actually have one in hand, right? We do. Okay. Once you have it, you're good. Awesome. Cool. The last team I was talking to doesn't have it in hand. And I was like, well, how do you guys plan on getting it here in a month? And she's like, well, we're in Canada. We live right next to the test and running plant. I'm like, okay, well, that's an exception. But you guys, okay, cool. Yeah, that's all the questions I had. Everything looks pretty good. I didn't see any crazy or any red flags. Yeah. Is there anything in your appendix slides you guys wanted to show that you guys worked hard on that I asked you a question on?
So that we worked hard on.
Okay. I remember sometimes I would have like a really complicated appendix. I really wanted to wait for the question, the aha question, but you don't have one. That's fine.
Anything you guys want to show?
I think something that'd be good to highlight, maybe the heat transfer calculations for payload for our cooling systems. Because I know we
Sure.
put a lot of work into that.
Wait, I don't think the calculations are in the appendix. My bad.
Never mind.
I'm so sorry.
I wouldn't be able to call anything out looking at it without like thinking about it for a while. So you could put anything in front of me for thermo, and I'd be like, yeah, that's about right, right? It goes away. Cool. Awesome. Yeah, you guys are great. This is a month away, so you guys are right on time. So, is there any other questions you had for me? I didn't get like I don't have anything from Ezra or the competition, so I don't know what I don't have anything else I got to give you or prove to you guys or whatnot, like, other than the design. But everything else here looks good.
Yeah, I think the only question or concern I had is that we saw, or we've been watching a lot of the like other I guess flight readiness reviews or video safety reviews that Ezra has posted. And we just noticed that they had RSOs or multiple judges or like kind of like a panel present. So we just wanted to make sure that we were okay with everything with just you being here and having this recording, and I'm sure we can like send it out to whoever needs to see it.
Yeah, I wasn't. Yeah, they didn't tell me to have anyone else on here. I wouldn't be surprised if they had a couple highlighted. The ones that are posting are highlighted because they have RSOs and a bunch of people on there.
Okay.
Yeah. I'm pretty. I usually do things pretty straightforward. If you guys, and the thing I'm worried about is you get off the ground and you're gonna come back in one piece, right? Like other than that, like as long as you're being reasonable, that's you're cool. But your recovery setup looks, awesome. Looks great. You guys are testing it, and your motor, those main points for me all look good. You're stable. You're gonna recover, and you're getting off the pad. So everything else is good. So, and if they require more RSOs, and they didn't let me know that, and I guess we'll do this again, but or they can just watch the recording, which is probably better. I know it's hard getting everyone together, especially are you guys in summer right now, or are you guys still finishing up the semester?
We're in summer right now.
Okay, yeah, cool, awesome. Well, I guess you guys pass, so you guys can rest your feet. So, I will go on my side and click on the button to get that through. So, if you can, please share a link of the recording with me, and so that way I can put that in.
All right, sounds good. Do you have any other questions for us that we can answer right now?
Nope. I will see you guys in about a month.
Awesome. Sounds good.
Yeah. All right. Awesome, guys. Congratulations.
Sounds good. Thank you.
Have a good
See you
night.
there.